Hello students, welcome back. Let's go back to section 3 and this time let's try to complete it. This completion will require 2, maybe 3 videos, and also it'll require linear algebra. Linear algebra I mean by Math 3330, some serious linear algebra. That's why I set these videos as optional videos. Okay, let's go back. Previously we discussed the general solutions theorem. Goes like this. L of y equal to 0, where L is the linear differential operator like this, or equivalently speaking, we have a linear ODE like this with variable coefficients. Then this ODE has n linearly independent solutions, y1, y2, y3, and so on. This one we proved, and then instead of going to the next claim here, we went through sections 4 and 5 and did a lot of applications on it. Now let's come back to this general solutions theorem, and this time let's complete it. However, a little bit of a review is in order, so instead of going to the next claim here, let's come back to this and redo this time. A little bit more in depth. We're going to be using the fundamental theorem of ODE yet again. A linear ODE has a unique solution under a given linear condition, given initial condition, excuse me. And to be a little bit more precise, there's interval of definitions and so on, but let's give it by. In any case, please remember, if you have a linear ODE and an IC, then there is a unique solution, one and only one solution. Okay, let's go. Here's a formal way to write the same thing. There are n linearly independent solutions, y1 through yn, or equivalently speaking, there are functions y1 through yn such that all these are solutions. L of y1 is 0, L of y2 is 0, and so on. They're all identically 0, so they're all solutions of the homogeneous linear ODE. And furthermore, they are linearly independent. Whenever their linear combination is identically equal to 0, all the coefficients, c1, c2, c3, they're all zeros. So that's a formal way to write the same thing. And the reason I gave you this formal writing, this part is not that important. I wanted to emphasize that we need this L of y for all these are 0, and also this part. We need this linear combination. Eventually, we have to prove all the coefficients are 0. Okay, this formal statement here actually gives you a roadmap where we start and where we want to conclude. Okay, let's begin. Such y1 through yn exist because of the fundamental theorem. This equation, L of y equal to 0 has a unique solution for given initial condition. So what if I give you n different initial conditions? Then I'm going to get n unique solutions. For each initial condition, we have one unique solution. So you're going to get n solutions, y1 through yn. The big question here is how cleverly I'm going to set those initial conditions. Ready? Here we go. These are the initial conditions. Let's see. Same equation part, ODE part is the same, L of y equal to 0. And then how about the initial condition here? Y of t0 is 1, and then the derivative, the second derivative, all those derivatives are 0 when evaluated at a certain point t0. And this is an IVP for linear ODE, so we have a unique solution. We're going to call it y1. Please pay attention to this color coding. Now here's a second IVP. This time, same ODE, but the initial condition is a little bit different. Y of t0 is 0, and the first derivative, y prime of t0 is 1, and all those other derivatives, y second derivative, third derivative, all those are 0 when evaluated at t0. And that has a unique solution, and that's y2. Similarly, we can consider this IVP, initial value problem, same ODE, and then initial condition is like this, y of t0 is 0, y prime of t0 is 0, second derivative is 1, and all the other derivatives all zeros. We can just repeat it. Here's the last entry there. Same ODE. Everything is 0. Original, first derivative, second derivative, they're all 0, except for the last one here. N minus first derivative is 1. So this IVP has a unique solution, and we're going to call it Yn, respectively. Consequently, we're going to get this. So Y1 satisfies this, Y2 satisfies that, Y3 satisfies this, and so on. And all these are unique solutions. We're not going to use uniqueness here, actually. So don't pay too much attention to unique part. They exist. That's sufficient for us. Now we're going to prove these Y1 through Yn are linearly independent. How do you do that? As usual, we start from the linear combination, set it equal to 0, and we have to prove all the coefficients here, they're all 0. C1, C2, C3, they're all 0. So from this linear combination, we have to deduce all the coefficients are 0. Now, here in the first line, you can see the first coefficient C1 is equal to 0. Why? You set up this linear combination identically equal to 0, and this is identically equal to 0 for all t, so you can plug in any t value. Why don't we select the t0, the t0, where the IVP started? If I do that, then y1 of t0 is 1, see here, and everything else here, they're all zeros. You see? Look at this column here. y2 of t0, y3 of t0, all these, yn of t0, they're all zeros. So this part just drops out, and we have c1 times 1 is equal to 0. Conclusion, c1 is equal to 0. Let's go back to the main statement in formal expression. There exist functions y1 through yn. Yes, they exist because of the fundamental theorem. And their solutions, again, yes, from the fundamental theorem. And then we want to prove they are linearly independent. So we assume linear combination is identically equal to 0. And my goal is to prove all the coefficients, C1, C2, C3, they are all zeros. So far we proved C1 is 0. And we have more to go, but as a matter of fact, we are almost there. We got up to here, C1 is equal to 0 from this linear combination and plugging in T0. Okay, here comes a second clever idea. The first clever idea is to set up these IVPs. Second clever idea is to take the derivatives. Take the derivative here from this linear combination. Derivative of right-hand side is of course 0 because derivative of any constant is 0. In the left-hand side, we are going to get this linear combination of the derivatives. And then let's plug in t equal to t0 because this has to hold for all t's. So if I do that, let's see, this is 0. Y prime of t0 is 0, of course. That's one way to see it. Or c1 is 0. We already proved it. In any case, this part is 0. Now, y prime of t0, that's 1. Look at this column here. And then all the other here's, they're all zeros because of this column here. y3 prime, y4 prime, all the way over to yn prime, all those derivatives have 0 when evaluated at t equal to t0. So all this part drops out. This one already dropped out earlier. So what do we have? We have c2 times 1 is equal to 0. The conclusion, c2 is equal to 0. Okay, so far we got c1 is 0, c2 is 0. What do you do next? Take the derivative again, and then again. Repeat it until you get to the last entry there. You see, if you get to the last entry, what are you having? The derivative, it's the same deal. We have a linear combination of the derivatives. Right-hand side, we have constantly equal to 0. And then here, what do you have? All these are zeros because you're looking at the last column here. All these derivatives, n minus first derivatives, evaluated as t equal to 0. They're all zeros. And last entry, that's 1. So basically this whole part, all these drop out. And what do you have? Cn times 1 is equal to 0. Consequently, Cn is equal to 0. We got everything. All these coefficients are 0. let's have a brief recap. We want to prove that linearly independent solutions y1 to yn exist. In other words, those functions exist so that their solutions, L of y1 is 0, L of y2 is 0, they're all solutions. Moreover, they are linearly independent, which means when we assume the linear combination is identically equal to 0, then we have to prove all the coefficients are 0. So that's what you want to prove in the end. They exist, these functions, and their solutions because we know they exist from the fundamental theorem. Now we are setting this one equal to 0, linear combination is equal to 0 to prove the linear independence, and eventually what you want to prove is all the coefficients Ci, C1 through Cn, they're all zeros. How did he do that? These functions exist depending upon the IVP, so we're setting appropriate initial conditions, and that's a clever idea number one. Set up all these, and then we have functions y1 through yn. Consequently, we get this kind of conclusion here. And then we start from the linear combination, and then plug in t equal to t0, and use the first column here to conclude c1 is equal to 0. And then we take the derivative, plug in t is equal to t0, and you use the second column here, so c2 is equal to 0. And then repeat the idea, take the derivative and use the third column. And so on. We repeat, and you're going to get all the coefficients, c1 through cn, are all zeros. So that completes the proof. So that's the first half of this general solution theorem. Now, how about the other half here? That's going to be a bit harder. Moreover, any solution L of y equal to 0, that y can be written as a linear combination c1y1 plus c2y2 plus all the way over to cnyn. Any solution can be written as a linear combination. Basically, we are getting the basis of the solution space. Okay? This one says the linearly independent family exists, and there are exactly n such linearly independent functions. They exist. We got it? Now they generate the entire subspace. So what do we have? We got the basis. So dimension of this solution space is n, and we have bases, y1 through yn are bases. If you take different bases, still you have to have the same number because dimension is fixed as n. And even if you use alternative methods to get y1 through yn, whenever they are linearly independent, then they are going to be the bases. You see? Basically, we proved, or we are going to prove, that y1 through yn is basis, and consequently, the dimension of the solution space is n. That's basically what this general solution theorem is talking about. We're halfway through. We proved the linearly independence. The other, spanning, not just yet, and that's postponed, because we need some lemmas. Let's go over to some trivial observation. This one doesn't really deserve to be called any kind of lemma or even proposition, just trivial observation. If y1 through ym are solutions, then their linear combination is also a solution. Actually, you know what? They don't have to be linearly independent, excuse me. Any solutions will do. And then any linear combination is also a solution. In other words, L of y1 is 0, L of y2 is 0, all these, L of ym is equal to 0. And whenever you have linear combination, and this number doesn't have to be equal to the order, so I should be using m instead of n. Sorry about that. Any linear combination is also a solution. How do you prove it? Well, as a matter of fact, it's just the repetition of this one. You see? Any linear combination of two solutions is also a solution. And just repeat it many more times, then you're going to get that m times. That's basically it. So the proof is left to the students. As a matter of fact, I did give you the proof here, but the details left to the students. Okay, that was just a trivial observation, no biggie. Now let's go to something big. This one really deserves to be called a lemma, a key lemma. The linear combination of the functions c1y1 plus c2y2 plus and so on is identically 0. That statement is equivalent to these column vector functions turned out to behave the same. The linear combination, the same linear combination with same coefficients c1 and c2 and so on, will turn out to be 0 identically. So this and that are equivalent. Let's make one trivial observation here. If you concentrate over the first component here, y1, y2, y3 all the way over to yn, that's exactly the same as the linear combination that appear here. So if this is true, then the first component, that should be true. The question is, what about the other components? Also, take by vice versa. If this matrix expression is true, then certainly it is true for all coefficients. All components, excuse me. True for the first component, the first line, true for the second line, true for the third line, true for the fourth line, all the way over to true for the nth line, if this entire thing is true. And this one is about the first line only, so this direction here, the if part is trivially true. You don't really need any proof because the first line is not other than this. And this one says not just first line, all n lines are true. So this one is actually a stronger statement. So you don't have to prove it. It's just a trivial observation. This one, on the other hand, the other direction, that requires some thinking. And that's what we are going to do. Indeed, let's go to the proof. And that's easy. All you have to do is concentrate upon the first component, and that's it. I highlighted in bold, and I'm using the color coding, so it's easy to see. Now let's go to the other direction. So, okay. So there you go. We assume the linear combination is identically equal to 0. And what do you do? Our bread and butter, we're going to take the derivatives. If you take the derivative, what do you get? Right-hand side is derivative of 0, so that's 0. And then left-hand side, we have to have the linear combination of the derivative. Take the derivative again, we get the third line, and then fourth line, and then take the derivative yet again, we get the nth line. Of course, this can continue forever, but I don't have to go for n plus 17 derivative. I can stop at n minus first. That's all there is. Consequently, we have this conclusion. Forward direction is done. Okay, that proves the key lemma. And if you apply this lemma and the definition of the linear independence, you're going to get this conclusion. What do you mean by linearly independent? Linear independence means if this linear combination is identically 0, then all the coefficients are 0. And what do you mean by these are linearly independent? If this linear combination, this one, is identically 0, then all the coefficients are 0. But then again, this linear combination, that linear combination, those are equivalent. So of course, the statement about linear independence must be equivalent as well. If you want a bit further explanation, they're all here. Linear independence means this, but then again, this pink highlighted part is equivalent to that, so substitute it and you get the linear independence of the column vectors. That's about it. Okay, let's stop here.